This is chapter 26 and 27. We're going to combine both chapters today and learn about the z-test for percentages. So just like everything we did for averages, we learned about how to do a large z-test for the average, and we learned how to do a two-sample z-test for the average. We're going to do the exact same thing now for percentages, and you'll see that our formulas seem very similar. So let's start with our large one-sample z-test for a 1%. We use this test if we're interested in the population percentage, and we have to have a large sample size. For preliminary work, you still have to find observed, expected value, and standard error. So all of our tests so far have observed, expected value, and standard error. Well, observed percentage, that's just what percentage did you see? What was your sample percentage? Your expected value for the percentage, well, our formulas in all of our chapters so far has been the expected value is equal to your population percentage. And we'll say there that's the population percentage if the null is true. So we have to assume the null is true. And the standard error for the percentage, well, remember our formula so far has been population percentage times 100% minus population percentage over sample size. And when I say population percentage, again, we don't know what that population percentage is, but we'll say that's the population percentage if the null is true. So whatever you write in your null hypothesis, that's the population percentage you use here for expected value and the one used in the standard error. Your test statistic then, just like before, z equals observed minus expected value over standard error. So it's the same test statistic, we just put percentages because we're dealing with percents. And p-value, once again, we're going to use the z, the standard normal table, to find our p-value. So if your alternative is less than, you'll shade to the left. Greater than, you'll shade to the right. And difference, you'll shade in both tails. So we don't, just a few remarks, we don't know the population percentage, but we assume the null hypothesis is true. So we use that value for all of our calculations. Also, we will only do a large sample z-test for percentages. You don't have to worry about what to do for small samples in this class. And finally, determining if the sample size is large enough, that's actually pretty complicated for percentages. So we're not going to worry about it in this class, so just assume that every problem I ask you for percentages is large enough. I'm not going to make you check or even really show you what it is, just because, again, it's more complicated than for averages. Okay, national data suggests that 25% of Caucasians have a certain gene. To see whether cash value people are similar to the nation with respect to this gene, a researcher takes a simple random sample of 200 people and finds that 39 of them have the gene. Is this evidence that the cash value people are different from the nation with respect to this gene, or is the difference due to chance error? So let's write down a couple things that they told us, like my sample size equals 200. Now notice it didn't actually tell me sample percentage, but it said 39 out of the 200 people. So let's actually calculate our sample percentage. So it'd be 39 out of 200. Now to calculate percentage, you divide the 39 out of 200 and then you times it by 100%. And just put it straight into your calculator. So 39 divided by 200 times 100. You don't actually have to push a percent sign or anything. That's just more like units, like saying inches or something. Gives me 19.5%. So that's my sample percentage. And then what do we want to know? We want to know, is the population percentage, it said, is it different? It didn't say greater than or less than, so let's just say different from what? Let's see, they're comparing it to the national average of 25%, so different than 25%. So that's the question. Now let's go through our steps. I took the time to go ahead and type out the null and alternative hypotheses here because you could word it two different ways. All of these just kind of mean the same thing, but remember again, I'm not the one that writes the exam, so you want to make sure that you can kind of recognize different ways she might write it. So you could say like the percentage of all people in Cache Valley with the gene is 25%. So remember the null is always like equals, it's always the status quo, nothing interesting. So it would just be that we're the same, so the percentage is 25%. Or you can maybe say the people in Cache Valley are the same as the rest of the nation with respect to that gene because they were 25%, so if we're the same, we're also 25%. The alternative then is that the percentage of all people in Cache Valley with a gene is not 25% or is different from 25%. Or you could say the people here in Cache Valley are different from the rest of the nation with respect to that gene. So 2 different ways she might word it. You're always going to be safe if you start writing it with the percentage, and then you could just kind of look through all of her choices to see what would match that. Okay, our test statistic, we have preliminary work. First, find observed, expected value, and standard error. So our observed percent, well, that would just be what did we see in our sample. Our sample percentage, we calculated as 19.5%. The expected value is equal to our population percent, which of course we don't know, but we go with whatever the null hypothesis says, so 25%. And the standard error for the percentage is square root, and it says population percent, which we're assuming is that null value again, so we'll do 25% times 100% minus 25%, all over my sample size of 200. Make sure everything ends up inside the square root. We should get 3.06%. Now you can find Z. Z is always equal to your observed minus your expected value over your standard error. And because we're dealing with percents, I can just put a little percent on here to remind myself what I'm working with. So observed is 19.5 minus expected of 25 over the standard error of 3.06. Gives me negative 1.797. So we are 1.79 standard errors away from our expected value. Let's look at our p-value. Okay, because up here we said that it is not. Anytime it's like not, if we didn't say less than or greater than, we're going to have to do both tails. Or this is a two-tail test, as our textbook would call it. So here's negative 1.797. Here's positive 1.797. And we want to find the area in both tails. Using the normal table, it only gives areas in left tail, so let's look at that negative 1.8. That will be easier. So Z equals negative 1.80. Looks like the area to the left is 3.59%. So this is 3.59%, which means the area over here is 3.59%. You want both tails, so find a total p-value. Is going to be 3.59% plus 3.59%, which is 7.18%. So that's my total p-value. Notice this is going to be a big p-value, whereas if I'd only had one tail, I would have ended up with a small p-value. So that difference between one or two tails can make a big difference. So you always have to pay attention. So let's interpret the p-value. The p-value is always, it's the chance of getting your sample data if the null hypothesis is true. So let's kind of write that down just to remind ourselves. So again, general definition, the p-value is the chance of getting our sample data that we got, or something more extreme, like something even farther out in the tails, if the null hypothesis is true. So in our case, that would mean there is a 7.18% chance of getting a sample percentage of, let's see, what did we get, 19.5%, if the population average is really 25%. Well, 7.18% chance, that's not too unlikely. Somewhere between 1 in 10, 1 in 20 chance. So it could be plausible. It could happen. So our conclusion is that this was a big p-value. So we fail to reject the null hypothesis. This means it is not statistically significant. And our final conclusion to give to our bosses, we would say, like, we didn't find enough evidence that what? And now you write your alternative hypothesis. So that the population percentage in Cache Valley is not 25%. So we're not really saying that it is 25%, just that we don't really have enough evidence to say that it's not 25%. And last, would it matter if I told you that the histogram of the box model was lopsided? So like when you look at percentages, if your population percentage is like small or big and you look at the histogram of the original box model for your original population, it's going to end up being lopsided. So the question is, would that affect us? Because I mean, we're using a z-curve, something's supposed to be normal here. Okay. Well, in our case, no, it won't matter because we have a large sample size of 200. Now again, I told you in this class, just assume all of them are large sample sizes. So if it looks like it's kind of big, just assume it's big enough. Okay. So basically, thanks to the central limit theorem, we can use the normal curve for percentages if we have a large sample size. So, won't matter, we can still do the test as long as we have a large sample size. Next problem, a magazine claims that 50% of young mothers say that finding childcare is a problem. A local childcare referral group takes a simple random sample of 450 young mothers in the area and finds that 210 say that finding childcare is a problem. Is this evidence that this is less of a problem locally? And we want to use a 1% significance level. Okay, so let's look at this. Let's find a few things. So we want to find our sample size, which is 450. And we need to find our sample percentage. Sometimes it will be given to you, sometimes you have to calculate it. So there were 210 people that said it was a problem out of 450. So 210 divided by 450. So you put in your calculators, divide, and you times by 100 to make it a percent. So 210 divided by 450 times 100 to make it a percentage. And that's going to give you 46.7%. And what was our question of interest? Is this an evidence that it's less of a problem locally? So we want to know, is the population percent less than, let's see, what are we comparing it to? We're comparing it to kind of that national or whatever it was that the magazine was claiming. So is our population percentage less than 450? So our null hypothesis would be that it's just kind of equal. So we would say the percentage of all mothers in this area is, sorry, not is less than, and this is the null, is 50%. Or kind of we're the same as everywhere else. And this would be, the alternative would be the percentage of all mothers in this area is less than 50% because we want to see if it's less than. So you could say it's less than everywhere else. Now for our preliminary work for our test statistic. Our observed percentage, well, that's just, what did you find for your sample percentage? We got 46.7. The population percentage, that's always based on if the null is true. So if the null is true, then our population percentage is 50%. And for our standard error, we'll use that 50%. That's the biggest thing, to remember to use the 50% and not the 46.7. And then we'll do 100% minus 50%. All over your sample size of 450. That seems like a very large sample size to me. We should definitely be good. So I get let me double check that. 2.36 as my standard error. Now I need z. Z is always equal to your observed percentage minus expected value of your percentage over standard error of your percentage. So our observed was 46.7 minus our expected of 50 over the standard error of 2.36. Should give me 46.7 50. Negative 1.39. So we are 1.39 standard errors away. That's not too much. I'm guessing maybe I'll get a bigger p-value. Z equals negative 1.39. And looking at our alternative, we want to know if it's less than. So this is one tail, specifically the left tail. We'll shade to the left. Let's go to our normal table, look for negative 1.39. Looks like my closest would be right here, so that's 8.08%. So my p-value equals 8.08%. Let's interpret that then. So remember, it's the chance of seeing our sample data, what we got, if the null is true. So there is a 8.08% chance of getting a sample percentage of, what did we get? We got 46.7% or less, because it's technically something more extreme because you shade all the way in the tail, if the null is true. So in our case, if the population percentage really is 50%. So if it's really 50%, we only have an 8% chance of getting our sample percentage. Well, 8% chance, that's really actually not too bad. It's not too small. So does the null hypothesis seem plausible? Yeah, you could probably believe something with an 8% chance happens. So yes, 8% chance is fairly likely. So I might believe the null hypothesis. So once again, this is a big p-value. So we will fail to reject the null. It is not statistically significant, because statistically significant means you have a small p-value. And our final conclusion would be that we just didn't find enough evidence to say that the true population percentage in this area is less than 50%. Like maybe it is, but we don't really have enough evidence to say that.